Hello, thank you for joining. Coatings fail, sometimes due to process variation, just as you're about to start production, or they fail in the application and the customer is demanding a solution as fast as possible. So this talk is about avoiding catastrophic breakdown by leveraging new methods that allow fast measurement analysis and optimization. Why do coatings fail? How, where, and under what conditions do they fail? How quickly can you fix it is the typical question. Where should you measure? What properties are important? With micro and nano indentation, you can obtain the information needed to answer some of these questions, but can you trust the 1/10 penetration depth rule for thin films? Instrumented scratch testing can also provide valuable information, but are you really measuring adhesion with it? Is there an easier way to set up your measurement design of your lab equipment? Once you have all this information, this measured property information, are you properly simulating your application? And how to feedback all the measured knowledge that you've collected into a fast optimization of the coating? Can you feed that information into the design of the coating rather than relying on empirical know-how? Coating design and development traditionally relies on empirically established performance testing, and this will always continue as a necessary part of development, but it's a very slow process if the performance test does not feed back into your coating properties design. And it can also be a very expensive process depending on the type of testing that you need to do to qualify your changes. It relies on empirically built knowledge and know-how that becomes increasingly complex with layered materials and ever-increasing complexity of solutions. Finite element analysis methods can also help, but they're very slow and they take even longer to set up models for increasingly complex designs. It typically models an idealized coating in order to make the method more computationally manageable. So here's a brief overview of several different software modules that allow you to solve some of these problems. So to solve failure, you need to go as local as possible. What do I mean by that? Well, it's like being a tourist in another country. You can go visit all the great tourist sites, but did you really find out what the locals are like? No. To do that, you need to have a beer at the local pub to really find out what they're like. Just don't drink too much. By leveraging measurement analysis and simulation inputs, the simulation and optimization software can provide this local information of the weakest link in your coding system. You need to start holistic with the right questions. So the first step then is to the problem definition. And what questions do we need to ask of our coding system in terms of the application and the environment that it's in? And even once those environmental and contact loading conditions are assessed, have you quantified how the properties of your system and its performance vary from manufacturing methods, whether it's the substrate manufacturing variation or the process manufacturing of your actual coding system? Then you need to consider about the optimal instrumented measurements to detect or measure properties of your coding system and substrate that is the real response of that system as you would expect to see it in the application. So by understanding both environment variation, manufacturing variation on those property changes, you can then optimize the measurement design to find the weakest point. And then you're ready for optimization and validation. So the first tool that we can leverage for this is the test optimizer. What it does is it allows you to select several different measurement methods and then find the optimal test conditions to make sure you get the information that you're really interested in, the local information. So as an example here is a Braucke-Vendor indenter tip. So we've selected indentation, we want to use a Braucke-Vendor indenter tip, and I want to make sure that I obtain the mechanical properties from indentation in the coating and not into the substrate. So this helps you overcome that 1/10 rule to make sure you're getting the right info at the right place. So as you select, it then calculates the optimum test conditions for that type of test. So in this case, it tells you the indenter tip rounding, the force range that will give you the information you're interested in, and the distance between measurements for your point of interest. Similarly, you can set it up, say, for a scratch test. So here, if you're looking for to measure adhesion, you want to make sure your point of interest is selected at the interface, and from there it'll go on and give you the recommended loads and roughness, etc., that you need to do a proper scratch test. The indentation module allows load depth curve analysis, and it fits those curves for both the loading and unloading portions to calculate all the errors. It even has a traffic light system that gives you an indication of how much information is contained within your coding layer or layers and how much is within the substrate versus the noise floor. So this gives you more confidence on making sure that you're getting the information you need from the region of interest. It provides more trust in getting those mechanical properties that you can then further use in simulation and optimization processes. So here you can see that it's doing the load and unload portion. It also calculates the errors on each of these portions separately, and also including the Oliver and Farr analysis. With this new indentation and stress analysis tool, load depth curves can be used to establish property profiles, including yield strength and stress. So biaxial and shear stress hypotheses are analyzed, and you can do either or a mix of. So on the vertical axis, we have the biaxial stress, and on the horizontal axis, we have the depth of our coding. So what we've done, if you look at that inset image, is we've made a Kalo wear scar and made a series of indents throughout that Kalo wear scar, and they've then plotted on this chart. Now, because we're using a normal indenter, we are limited to only calculating a reference stress to a chosen reference point. And that's on the left side of the chart there, circled in red. That's how one of those measurement points near the edge of the crater was chosen. As we approach the interface, you'll see an increase in the biaxial stress toward the tensile direction. Now I'm showing the errors that have been calculated for each data point, and within the plateau region on the left, we have approximately a 1% error. So those spheres are showing both error in the unloading curve and error in the loading curve. The reason for that high scatter is that because of the thin coding in this region, we had to use a lower load in order to make sure that we didn't get too much substrate information. However, at the low load, the roughness of the coding in that area from the Kalo grind was proportionally higher, and that led to much higher error in those measurements. Absolute stress is also possible to measure if we were to use a mixed load indenter rather than a normal load indenter, because then it can actually calculate the Poisson's ratio at each of these local points, and from that we can calculate an absolute stress rather than relative. We made 3 indents per depth location. Then on the right lower image, you see all these curves, and you'll see the lower loads we used, which correspond to the indentations in the thinner region of coding toward the interface. A key point of using the Kalo method is that it's critical to get a smooth Kalo wear scar, low roughness, to minimize the errors. So here are some results of 2 different recipes for cathodic arc coding. The recipe 1 on the left is showing a constant yield strength and a constant biaxial stress as we move from this coding surface through to the substrate interface. Now what's interesting is by just changing the process conditions, we get a decreasing yield strength toward the interface and a decreasing or reducing compressive stress toward the interface. So in summary, the key features that are different from other methods such as Fib DIC milling, X-ray diffraction or nano XRD diffraction, predominantly low cost and industrial accessibility. So then it's just a matter of leveraging this software to extract this information in-house, keep your IP in-house, and do a much faster turnaround time on your design optimization cycles. The other key point is using just a normal load indenter. We are locally measuring stress, Young's modulus, yield, and strain at each indent location. Whereas with the Fib and X-ray methods, they are assuming a constant Young's modulus. If you actually have a modulus and yield that are changing through the depth, then that could lead you astray. With scratch analysis, that module allows you to optimize your coding performance for adhesive and cohesive failure with the effects of surface roughness included. So here's an example of optimizing the scratch test and the coding to withstand a desired load. So on the left, we have an animation showing a 200 micron tip or a scratch tip loaded onto a single layered coding system. And you can see that the maximum load shown in red is within the substrate. And in this case, we're showing the maximum stress now positioned at the interface for an ideal scratch test. The Film Doctor simulation tool allows you to do extremely fast calculations, and you can start with a known material solution. So you may have your a well understood coding system that you use and you apply on several known substrates, and now you want to know what its performance limits will be. Well, with the Film Doctor tool, you can put all your information in of your contact conditions and your material properties and find out how it will perform under a changing environmental condition. Or you can start with the desired performance for the application and work back to find out what material properties would give you that performance. So the calculations take seconds instead of hours or days for finite element calculation time, and just minutes of setup time, and you can go back and change them in another minute or so. It's extremely quick to go and change that. Now, it's more of a manual search tool to try to find and optimize. Now, the Istress module allows you to do automated intrinsic stress profile optimization. So basically takes what you would do with a manual search with the Film Doctor, automates that so you can now do many different combinations, but you can do them extremely quickly. The critical load optimizer allows you to automate the search for solutions within desired boundary conditions. So it might be that a customer comes to you and it's a solution that you've never had to offer before, a substrate you've never tested with before, and you're not sure if one of the coatings you have in your suite of coatings will be suitable. So what do? Well, if you can learn as much as you can about the contact conditions, you can enter those into the software and then determine which of your coatings that you may have on the shelf might be best suited, or what would you need to do to tweak those to make them better suited. So just to show you the simplicity of this tool, we've had a 14-year-old intern using the software, and he decided he wanted to try to solve the medical implant failure problem. And he wanted an implant that would last for a patient's lifetime, because a coating failure on an implant means a second operation for the patient, as well as all the pain and trauma that they have to go through. So he's showing there his solution on the right, which is the current versus the mechanical properties and stress profiles that he found would solve that problem. And he's going to publish that shortly. And this approach has several key advantages over state-of-the-art. It's extremely computationally efficient, faster with much less compute power. So I can run these calculations in a few seconds using a 1.6 gigahertz laptop. The calculations are based on real measured properties of your coding system, because it's the response of your actual system with its microstructure as it was grown in your coding chamber. The theoretical background is published in Wiley, and the book is called Applied Nano Indentation to Advanced Materials. So the chapter is chapter 22, and it's by Norbert and discusses the method. So in summary, indentation results can be leveraged for increasing knowledge of potential failure modes, even with very thin films. Property profiles are measured in local regions with more clarity that better simulates real contact conditions. So in summary, we leverage indentation for stress and other interesting property profiles to inform better materials and process design at a rapid development pace. Indentation and scratch data can be leveraged as design inputs. The simulation is based on real measured response of your system in question. The optimization process uses the measured information to forward predict when the system will fail based on a change of conditions. So we provide consulting services for residual stress measurement, and with this KLO and indentation methodology, we can do scratch test analysis and optimization, real application simulations based on the measured properties, and then we can help you design functional materials solutions for layered systems and then optimize those for various application constraints. And we also offer software service and support for SIOMech. Thank you. I'll be available for questions after the talk, and my contact details are listed below, along with Frank Pappas, if you're interested in finding out more.